Our last theoretical explanation for the three-fourths power law involves a variation on the surface law. You'll remember that the surface law predicted a two-thirds power scaling of metabolic rate with body size. This was predicated on the assumption that metabolism is constrained somehow by an exchange of something with the environment. In the case of the surface law, the important exchange was thought to be heat across the surface area of the body. The model I will describe now is motivated by that same presumption, but now it's centered around the exchange of things like respiratory gases, nutrients, and wastes. This model assumes that the three-fourths power law is the result of a so-called fractal scaling of metabolism with body size. We have to establish what we mean when we say fractal scaling. Let's take a simple shape. A sphere is as good as any other. If we look at the scaling of surface area to some fundamental dimension of this shape, let's say its radius, we see that the surface area scales to the 2 power of the length dimension. Now let's look at the volume. Similarly, the volume of the sphere should scale somehow to the 3rd power of the length dimension. If we look at both of these scaling exponents, we see that they are integers. That is, the scaling of surface area to length is to the power of 2 exactly, and the scaling of volume to length is to the power of 3 exactly. Fractal scaling differs fundamentally from this integral form of scaling. The meaning of the term fractal comes from the scaling exponent being a fraction rather than an integer. In other words, fractal scaling is scaling to fractional dimensions, not to integers such as 2 or 3, but to values in between. We have to clarify this a little bit. Let's take our sphere again. We've already established that the surface area scales to the power of 2 of the length dimension, and volume scales to the power of 3 of the length dimension. This is integral scaling. But let's take the case where we predict the exponent for scaling of surface area to volume. We've already established also that surface area scales to the 2/3 power of volume. 2/3 is not an integer, but this kind of scaling is not fractal scaling. It's not fractal scaling because the ratio 2/3 is a rational number. That is, it is the quotient of 2 integers. This can ultimately be reduced to the integral scaling of surface area and volume to the fundamental dimension of length. This is not the case for fractals, however. Fractals are a special kind of geometry in which similarity is preserved at all scales, even if the shape is not. Here's an example of a fractal shape. We start with a triangle, and then we add a smaller triangle at each of the 3 faces. Then we add another triangle at each of these new faces. We could carry on indefinitely with this. I'm not going to, but you can look up lots of examples of fractal shapes on the internet. This particular one is called a Koch snowflake. This developing shape has a property called self-similarity because the same shape, in this case a triangle, is added to the faces of the vertices no matter how fine the vertices might be. At every scale you can look, you see this same triangular form. The development of these complex and beautiful shapes does not tell us why this is called a fractal shape, however. To see why, we have to look at a scaling relationship. Let's plot out a simple one, in this case the log of the length, basically the sum of all the faces of our Koch snowflake, and the area contained within it. Let's lay out a couple of scenarios for how these two quantities could scale with one another. The obvious scaling relationship would be that the area scales to the 2 power of the length, that is, the slope of the curve, which is the exponent in the power equation, should be 2. Now let's take another scenario. Let's presume that the area doesn't scale to the 2 power of length, but scales to the 1 power of length. There are circumstances where this can be the case, for example, where you have a flat leaf or any other kind of flat morphology. In this instance, the area will actually scale to an exponent close to 1, that is, the area will be directly proportional to the length. However, if we plot the area enclosed by our ever-increasingly complex Koch snowflake, we'll see that the scaling exponent is situated somewhere between 1 and 2. In other words, the scaling exponent will be some fractional value. Furthermore, the fractional value cannot be reduced to a simple integral scaling, as was the case for, say, the scaling of surface area to volume. In other words, the area scales fractally to the length. Now, there's an interesting geometric interpretation of this. Bear with me because we again have to let our imaginations run loose a little bit. In this fractal scaling relationship, what we have here is a line, namely the outline of the Koch snowflake, expanding in such a way that it approaches the scale of an area. In other words, the fractal scaling of an object like the Koch snowflake produces a shape where the outline becomes as much an area as it possibly can be without becoming an area itself. It can approach a scaling exponent of 2, but it can never quite get there. The same kind of fractal reasoning can apply to three-dimensional objects as well. So, for example, the Koch snowflake could expand in 3 dimensions as well as 2. Now it becomes a surface enclosing a volume. And just as a 2-dimensional fractal scaling can represent a line that seeks to fill an area, if you will, 3-dimensional fractal scaling can represent a surface that tries to fill a volume as much as it can. In this instance, the scaling exponent of surface area to volume will range somewhere between 2 and 3. Okay, at long last, we're ready to begin thinking about what this means for the 3/4 power law. Metabolism basically is a flux of energy and materials across the boundary between the interior and exterior of an organism. These exchanges are going to be limited somehow by surface area. Now, if we look at a lung, here's a photograph of a resin cast of the airways of a lung, we see that there seems to be fractal scaling going on here. The lung's airways divide into ever finer and ever more numerous passageways, each of them terminating in one of the several 100 million alveoli that serve as the exchange surfaces for respiratory gases across the lung. In other words, the lung surface area seems to be built to be a volume-filling surface area, just the kind of thing we would expect for a fractal scaling relationship. So, how does this translate into a 3/4 power scaling for metabolic rate? Here's the general idea. Let's imagine we plot lung surface area, that is the exchange capacity of the lung versus body mass. Again, we imagine a couple of possible scenarios. In the first, we assume that lung surface area scales isometrically to body mass. That will produce a scaling curve with a slope equal to 2/3, that is, where the scaling exponent is 2/3. As you'll recall, this is not fractal scaling. The alternate scenario is to imagine that lung surface area scales to body mass directly. That is, the scaling exponent of surface area versus body mass should be equal to 1, which is tantamount to saying that it scales proportionally to the body's volume. This is the scenario we would expect if total body metabolism was simply the sum of all the cell's metabolisms added together. Fractal scaling comes in because lung surface area can never scale as if it were a volume. It will always have to scale to some exponent less. Thus, we would expect some sort of fractal scaling of the lung surface area. Specifically, we would expect the scaling exponent to be some value greater than 2/3 and less than 1. 3/4 is right in that range. But why 3/4 exactly? Well, that's still a bit of a mystery. One can, for example, derive an exponent of 3/4 from the kind of fractal scaling we would expect in a ramifying blood vessel network. That's an exchange surface too, just like the lung, and we would expect fractal scaling there as well, and for the same reasons we would expect it in the lung. The trouble is, one has to make assumptions about how blood vessel networks scale in order to derive the specific value of 3/4. So, for example, if we assume that the aggregate cross-section area of all the blood vessels at each level in a network is constant, we can get a value of 3/4 scaling for metabolism. We know from Murray's law, however, that this is not true. The assumption of constant aggregate cross-section area is tantamount to saying that the sum of the squared radii is constant across all levels of the blood vessel network. Yet Murray's law shows that it is the sum of the cubed radii that is constant rather than the sum of the squared radii. So we still cannot quite get to the value of 3/4. No matter what the real explanation, though, it's clear that there is something interesting going on here. In fact, there may be more than one factor operating to produce the scaling exponent of 3/4. Nevertheless, there are many significant implications for physiology and evolution of energy use that follow from this particular scaling relationship. Let's have a look at some of those now.